Hey guys, this is Mrs. Cribb, and this is going to be an introduction to reaction rates. There's not actually going to be any math in this for general chem students, so maybe you'll be celebrating at this point. All right, we're going to start off by going through some of the notes, and I'll be flipping back and forth between the notes and the Prezi for this chapter, which I'm pulling it right here. Chapter 14, reaction rates. So you'll have to forgive me for just going back and forth a little bit. All right, kinetics is what this chapter is about. Now, kinetics, remember what kinetic energy is? Kinetic energy is the energy of movement. So kinetics is the study of rates of reactions, or basically how fast you can do something, how fast you can make something. And it also talks about the steps that we need in order to make something happen, so the steps by which they occur. Thermodynamics is what we had in chapter 13. Remember, therm means heat, and so it's dynamic means changing. So thermodynamic is the change in the heat of reactions, and it will answer questions like, will a reaction actually happen? Kinetics answers the question, how fast. So there's the difference, okay? Thermodynamics deals with heat changes and will the reaction happen. Kinetic answers how fast. So like, how much kinetic energy do you have? How fast are you moving? If something is thermodynamically favorable, it may still not happen automatically. And some reactions need a push to get going. Now, here's some examples of thermodynamically favorable conditions. Exothermic reactions, which we actually covered in the previous chapter. Remember, exit, it's the therm exiting, it's the heat exiting. It feels hot to you. These are like hand warmers. And in exothermic reactions, we have that negative value for delta H. So maybe negative 2012, 2220, oh man, 2219 joules. I was actually thinking of a value there for one of our examples. So that would be exothermic reaction with a negative delta H, and you would write that in the product side. Okay, and so we covered this in the last chapter. One thing we didn't talk about a lot is entropy. An entropy is an increase in entropy, that is also thermodynamically favorable. It happens naturally. Nature tends toward disorder. Your room tends toward disorder. My notes tends toward disorder. Things get more and more messy, and in all of nature tends this direction. And so we're going to stop for a second and look at a video about this. So here's the Prezi on reaction rates. Of course, a Quizlet is embedded within the Prezi, so you always go there, click on it, and it pulls up the Quizlet. At some point, we will do some review exercises. It has all the terms for this chapter. It has terms that only honor students have to know, just because I did not separate them out for this particular thing. So if you come across terms that are not included in your notes, don't worry about that, or not included for you to know. All the terms are in everybody's notes, but honors just has to know more than the other. Again, that's because I used to teach this entire chapter to everybody, but I'm not now. So once we get past the Quizlet, here's the first video. We're going to watch a few more videos this time since I'm not there, and we got to get a good bit of a review coming. Okay, let's rewind this for a minute. And before it starts, let me see if I can get it to pause for a moment. Remember that any song in a Prezi that you memorize and sing in front of me is bonus points. So far nobody's done it, but that offer is always on the table.
Engineers have a great big need to control chemical reaction speed. Faster, slow, which is to be the fate. How can we change the reaction rate? Reacting molecules to collide. Angle and energy will decide if the reaction will proceed at last, and if that reaction will be slow or fast. It's rate of reaction. Reactants for products at a certain speed. It's rate of reaction. How do we get it to serve our needs? Add or remove some steps. Make more collisions or less. Slow down or speed it on up.
I'm going to pause it for here just for a moment. because if you look at your notes on the next page, well, I guess maybe page 3, it gives you a list of the things that it says 5 most important factors affecting reaction rates. That's in 14.6. You don't have to necessarily look right this second, but everything in this song is listed in the notes there where it says 5 most important factors. So this song is actually full of a lot of content. So if you memorize this song, you'll have learned a lot of the things that you need to know for this chapter.
Some reactions happen way too fast. They can end in an explosive blast. To slow it down, you can add some steps. Use an inhibitor, then raise is less. Lower concentration or the temperature. Fewer collisions over time occur. Lower pressure if you have a gas. Less surface area for solid mass. It's rate of reaction. Reactants for products at certain speeds. It's rate of reaction. How do we get it to serve our needs? Add or remove some steps. Make more collisions or less. Slow down or speed it on up. If a reaction is too slow for you, here are a couple of things to do. Add a catalyst and steps remove. Get that reaction running really smooth. Make more collisions happen over time. Concentration and temperature increased, it's fine. Raise the pressure on your gaseous friends, or crush a solid, you will meet your ends. It's rate of reaction. Reactants for products at a certain speed. It's rate of reaction. How do we get it to serve our needs? It's rate of reaction. Change the mechanism, change your steps. It's rate of reaction. How many collisions happen more or less? Change your reaction speed. Make it fit your needs. Slow down or speed it on up.
Alright, yeah, see, that was pretty good. Alright, let's move on from here. So kinetics, this is what we just went through. The study of rates of reaction and steps by which they occur. Thermodynamics answers will. Kinetics, how fast. If it's favorable, some things will not happen automatically. The favorable conditions, which you need to make sure you know, are exothermic, which means your delta H, or change in your heat, is negative, or you increase your entropy. And that brings us to 14.2. So I'm going to go back to our notes. Whoops, wrong place. 14.2. Energy diagrams. Thermodynamics relates only to the starting and ending point. So please remember that. Thermodynamics relates to where you start and where you end. Now let me give you an example. If I'm going to leave my house and travel to TKA, so here we go. Here's my house. And I get in my car. I'm a really, really good artist. And I drive and I go to school. TKA is way over here somewhere. Alright? Alright, now maybe I go this way. I go and I travel around. I come up and down. I go over here. Oh, I stop and look at this beautiful tree. And I go over here. And then I finally go up the hill and drive around and I park right there. And I go in the high school building. Alright. So thermodynamics would only care that I started off at my house and I ended up at TKA. And it does not care that I took this long, weird path to get there. It's just the beginning and the ending. It's basically the beginning, the reactants, and the products, or the reactants and the products. But kinetics cares about how I go. Kinetics measures the pathway. How long does it take me to get there? What can I do to shorten my pathway? So kinetics would be much happier if I took a short path. I got in my car and I went, bam, TKA, around the corner, and I parked. I got there a lot faster. So kinetics compares the two pathways. It measures the beginning and the ending. All right. Now this is, we've seen this formula right here from chapter 13. Delta H, remember that's enthalpy, H for enthalpy. The delta H is it's the sum of the H of the products minus the sum of the H of the reactants. It's the enthalpies of the products minus reactants. And we talked about that, and I told you there's a video there was a little bit of introduction to activation energy. That last chapter, it wasn't important. This chapter, it is important. Before, we only dealt with the beginning and the end. Beginning and the end. And that was thermodynamics. Now kinetics is going to mess with this part in the middle, the activation energy. So what I want you to do, this is already written into your notes. If you'd like to draw a little picture about pathways, that's fine. But we're going to talk about activation energy more as we move on in this chapter. And in the next chapter, I believe. All right, now, collision theory. Collision theory says that particles must collide before they can react. Well, that makes sense. I can't, if I bring some hydrogen and some oxygen, and they're just kind of floating around out here, hydrogen and oxygen, and they don't ever come in contact, they're not ever going to actually react. So they have to hit each other in order to react. And not only that, they have to be oriented correctly. That means they have to hit each other in the right way. Otherwise, they won't react. And they must have enough energy. So if they barely tap and bounce off each other, it's not going to be helpful. So any factor that will increase, these are called effective collisions. Any factor that's going to increase these effective collisions will increase how quickly something reacts. Okay? So let me go back over here. There's this picture again. And notice that I put favorable right here because the exothermic reaction was favorable. So in your notes, that's one thing you should do. This is the favorable reaction. That was a bad drawn circle, but this one is favorable. So make a note of which types of reactions are favorable. Exothermic, where the heat of the products is lower than the heat of the reactants. All right. Now, there's a couple of videos in here for review. This first one I'm definitely not going to do because it's boring. Let's be honest. It's just boring. It does talk about endothermic and exothermic reactions. But this one, we're going to go ahead and watch this one. And after we do that, we're going to practice a little bit of collision theory in the classroom. So skip the second video here. We're going to go to video 3.
We're used to our universe behaving in a certain way. There is a natural progression of events, of causes and effects. Living creatures and physical objects behave according to the laws of motion, quantum mechanics, and relativity. But there is something else at work here too, a natural phenomenon that affects the fate of everything in our universe. We are capable of building amazing and complex structures, but everything that we create eventually decays and falls apart. Living organisms age and deteriorate over time. A man preparing a delicious snack becomes distracted. A glass of milk falls and breaks. We've all seen this before. It's unfortunate, and it leaves a mess that his girlfriend now has to clean up. I mean, that he offers to clean up. But why does this happen? Well, aside from carelessness, that is. Why don't we ever see the opposite? Why don't we ever see shards of broken glass fused together and combined with liquid to create a full, unbroken cup? According to the laws of physics, this is technically possible, but we all know from experience that this isn't the way things work. In fact, every glass cup ever made will ultimately share the same shattery, broken fate, whether it's in a dumpster, recycling plant, or on your kitchen floor. It's the natural way of our universe, and it's all because of something called entropy. Okay, so let's just get right into it. What is entropy?
Well, there are several different definitions. I would say that entropy is, first of all, a measure of disorder. It's a measure of how many ways you can reorganize a given system.
The entropy of an ideal gas, for example, can be expressed with this equation, where S equals entropy. Kb is the Boltzmann constant, which is 1.38062 times 10 to the minus 23rd joule per... You know what? Let's just say you're playing a game of pool. A typical game begins with the balls arranged in a highly ordered configuration. This is a low entropy state. As the game begins, however, the ball...
Okay, that was a low entropy state because it was very orderly. So entropy is a measure of disorder, so the messier it is, the more entropy. The more orderly it is, the less entropy there is.
Balls are quickly scattered. The disorder of the table increases, and so does the number of possible configurations. Therefore, the entropy of the pool table has increased.
Now try to do the opposite. With a single shot, put them back in order.
Let's go to the bar. I'm gonna try that all day.
Might take a lot of points.
Yeah. Technically, it's not an impossible task, but it's extremely unlikely and something we probably won't ever see in our lifetime. Well, most of us at least.
By the way, I'm not advocating going to a bar, but this is just a fun video.
This natural tendency of entropy to increase over time is described by the second law of thermodynamics.
The second law of thermodynamics will tell you that the entropy of an isolated system cannot decrease as a function of time. So as time goes, it will either remain the same or increase.
A perfect example of this is life. A living organism is a highly ordered, low entropy system. And life, on this planet at least, can pretty much pop up anywhere we look, even from a rough, chaotic environment. But this order does not come without a price. It takes a lot of energy to lower the entropy of a system. In the case of plant life, most of this energy comes from the sun. And the sun is constantly radiating energy into space, increasing the entropy of our entire solar system. A hot cup of coffee has higher entropy than a cold cup of coffee because hot water molecules have more movement than cold water molecules and are therefore more disordered. Ice has even less entropy because of the restricted movement of water molecules in a solid formation.
All right, I want you to stop and notice this too. The entropy of ice is low. That means it's very orderly. The entropy of water, hot water, is high. That means it's very disorderly. It's messier. It's boiling over and the water molecules are flying around everywhere. So the colder it is, the lower the entropy is.
We all know that a hot cup of coffee will cool over time, and it's delicious. But be careful, hot, 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 hot. As it cools, its entropy will actually decrease. However, a coffee cup is not an isolated system, and the only way it can lower its entropy is by releasing its heat into the room, thereby increasing the total entropy of the surrounding environment.
Okay, do you get that? This is a funny place to stop. So, when a coffee cup cools off, its entropy decreases because the colder things have more order. But what it did is it gave its heat to the rest of the room. Remember, heat travels from hot to cold. So it gave its heat to the rest of the room, so the entropy of the whole room increased, which is normal. That's what happens in the universe. Entropy is slowly increasing.
Getting a haircut is another example of taking a disordered system and transforming it into an ordered system. A sexy, ordered system. However, even though the entropy may be lower on your head and face, according to the second law of thermodynamics, the overall entropy of the entire system must have increased. The barber burned calories to operate the scissors. Fossil fuels were incinerated to provide electricity for the clippers. And the hair that was removed was chaotically dispersed across the floor, only to be swept up, requiring even more energy. But why is this? Why must we live in a universe where disorder is constantly growing, and order is so hard to come by?
It's a very good question. It's not something that follows from the basic laws of physics.
Okay, now I'm going to stop the video right here. They do go a little bit into some evolutionary theory towards the end of this video, but this is one of those times we need to learn to take the good and from something and leave the bad. They're going to talk about the Big Bang Theory and evolution, and we're going to let that go because we know that God has the power to decrease entropy, which He totally did when He created us, when He created the universe, when He created people. He went against the law of thermodynamics. He created something very orderly, but it took Him doing it. Naturally, that would never happen. All right, now we're going to move on. So collision theory, I talked to you about this, and the particles must collide, they must hit correctly, and they must have enough energy. And if I was there, I'd show you a little physical thing to do with it. But we're going to look at this picture right down here, and then we're going to have we're going to pause the video and do a physical demonstration. So here we have two molecules that are going to try to react. All right, so this molecule and this one, they hit each other and they bounce off. And the reason is they're moving too slowly. They don't have enough energy. Here, the reactants are not facing the right direction. See, over there, the carbon was this way, and the carbon's on the other side here. They're not facing the right way. They're not oriented correctly, so there was no reaction. And on the third one, they have enough energy. Notice the energy amount, these little squiggle lines show you how much energy they have. So they have enough energy, a good amount of energy. They're facing the correct direction, and so they collide and they form new molecules. Looks like nitrogen dioxide and carbon dioxide. All right, so now we're going to pause the video and do a quick demonstration with this. Once you finish the demonstration, go ahead and we'll restart the video. Okay, I'm going to assume that you restarted the video. So now we're going to talk about, whoops, too far. We're going to talk about activation energy and the activated complex. So let me go back to this one. All right, there's the people demo. Activation energy, the activated complex. The activation energy, the E sub A, right here, is the energy needed to get the reaction started. Really, it's the minimum amount needed. Minimum amount needed to get it started. It's the initial push. This is the minimum amount, that's what it says, of kinetic energy that must be possessed by the colliding molecules before they can react. Remember this, reactions take place in two steps. First, you have to break bonds. And when you break bonds, that's always the endothermic process. You have to put energy in to pull things apart. They don't just fall apart on their own once they're bonded. You have to put the energy in and actually pull them apart, and then make bonds. And making bonds is always an exothermic process. And when you compare those, exothermic process, when you compare those, that determines if the overall reaction was endothermic or exothermic. Now we're going to draw this next picture. It's in the Prezi, and we're going to also draw it in your notes. So I gave you a big space to draw it in. What we're going to draw is, we're going to go ahead and draw an exothermic reaction. So, and this is going to be basically time that's happening. And we're going to start off with some reactants, and they're going to have a lot of energy. So this will be our energy in joules over this side, on this side, on the y-axis. And then they're going to have a hump, and then we're going to have the flat area down here. All right, and we're going to use this general equation and put them. Now, remember that we start off at the beginning, no time has happened, no 0 seconds down here. Before we do anything, we just have two reactants. We haven't actually put them together. So right here, I will have A2, and I'm going to draw it as A bonded to A and B bonded to B. So that's A2 and B2. These are the reactants. All right, I'm also going to put some arbitrary numbers. So let's just go across here. And we're going to call this 10 and 20, 30, 40. Well, this is not exactly right, but we're going to call this 50 up here. Okay, and these are joules, 10 joules, 20 joules, 30 joules, 40 joules, and 50 joules. Okay, so we start off with our reactants, and let's say that the heat of the reactants is 40 joules. And then I'm going to push, here's the area, I'm going to push the reactants up this hill and get them to up to here. Now the amount of energy it takes for me to push the reactants up this hill, that's called the activation energy. So this area right here is your EA, your activation energy. Remember that, EA is activation energy. All right, so that I push it up the hill, and when I get to the top, I make something called the activated complex. And the activated complex is going to look like this. We're going to have A, and we're going to have the B, and the A and the B, just like down here. But instead of having these solid lines bonding the A's to the B's, we're going to cause dotted lines to happen, dotted lines. And the dotted lines are going to happen between all of them. Now that's difficult to see. It's A with dotted lines between A with dotted lines between B with dotted lines between B, and dotted lines in the middle. This is the activated complex, or the transition state. I'm having trouble. Activated, there it goes, complex. And it's a transition state. It's what happens when you're getting ready to change over, okay? So at the top of the hill, the activated complex sits, okay? Now, if I was rolling a ball up a hill, when I got to the top of the hill, the ball could either go forward or it could go backwards. So the transition state is unstable, and it can go in either direction, okay? But we're going to pretend this time that it goes forward. So it's going to roll down the hill now, and I'm going to make the new things at the bottom. And so I'm going to draw the A's and the B's again, just exactly in the same place that they were at the very beginning of the reaction. But now I have broken the bonds between the A's and the A's, and I've made bonds between the B's, A's and B's. So notice here, in the transition state, these bonds are breaking. So they're not here. There's no bond right there between the A's and the B's. And in the transition state, these bonds are making. So we're breaking the red bonds, that's between the original reactants, and we're making bonds between the products. So you'll notice we have two ABs in the product side. There they are, two of them, two ABs. And on the reactant side, we had an A2 molecule and a B2 molecule. All right, this is the activation energy, the energy that compares the very top of the hill to the energy of the reactant. So notice that the activation energy compares the energy at the top, which is basically 50 joules, to the energy of the reactants. So the activation energy in this case is 10 joules, because that's the difference between here and here. It's 10 joules. That energy is the amount of energy I have to put in the system to make this reaction happen. And then the energy comparison between here and here, this is what we did in the last chapter. This is your delta H, because delta H only compares the reactants to the products. These are the products down here. And remember, delta H, what is the formula for delta H? It's the H of the products minus the H of the reactants. So the products H was 10 joules, and the reactants here are 40 joules. So in this case, it would be a negative 30 joules. So it's exothermic. And that's what happens here. When it's exothermic, the products are lower than the reactants. Okay, I want you to put this all into your notes. So if you need to pause for a moment and get that in, go ahead and do that. And then we're going to move forward. Notice that it says here too that the activated complex at the top is very unstable. It's short-lived, and it can break up to form products or to reform reactants. So that's what I said. The activated complex sits at the top of the hill. It can roll down to form products, or it can roll backwards to form reactants. If the activated complex goes on to complete the reaction, a large amount of energy will be released in exothermic reactions. And this energy, now listen to this, this energy that's released in exothermic reactions is used to start the next reaction. In other words, look at this again. When I start the reaction, I have to push it up the hill. But once it starts, this is going to release all this energy, all this negative 30 joules. That pushes the next ones up the hill. So it gets going at that point. A large activation energy, though, can prevent a favorable reaction from happening. One example of an activation energy is for us adding the heat to burn something, like a paper. If we're going to burn our paper, I'd have to light the paper. That's adding in that energy. But once I get it started, I don't have to keep lighting the paper. The flame spreads throughout the entire paper, and it keeps going until the paper's used up. I just had to put that first spark in there to get it started. That's the activation energy. All right, let's go back to our Prezi.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 39. It's activation energy. Imagine if I try to roll a ball up a hill. If I get enough energy into that system, the ball is going to roll down the other side. In other words, there was a certain amount of energy that that ball had at the beginning. We'll call that potential energy, and then we've lost some of that potential energy. But the ball just didn't go there on its own. I had to put a certain amount of energy into it. And in chemistry, we call that activation energy. Now, it's not only balls rolling up a hill and down the other side, it's chemical reactions. You can think of this as the reactants on this side, and this as products on the other side. And so we're only netting this amount of energy between here and here, but there's energy that you have to put into the system. Let's say we have an endergonic reaction like this, one that requires energy. Well, I'm going to...
Okay, endergonic or endothermic is what we've been saying. Here, the activation energy is still the comparison between the reactants and the top of the hill, but the products are going to have more energy inside of them. They don't let go as much.
Put more energy in, I'm going to get some of that back. If we were to look at the energy change, then everything above that is going to be the activation energy. What if I don't have enough activation energy? Well, I can put some energy in, but if I don't have enough, then it's going to go back to where it was before. And so activation energy is how much energy you have to put into a system to have a chemical reaction occur, and it's based on collisions between molecules. Most of those are unsuccessful collisions, and that's because they maybe don't have enough energy or they don't have proper orientation. But if they are successful, which again is incredibly rare, then we can have chemical reactions fire off. In a unimolecular reaction, that's mostly going to be interactions between the molecule and the solvent or background molecules. But if it's a bimolecular or termolecular reaction, it's going to be with other molecules or reactions with other molecules. In either case, it's going to be based on the Maxwell-Boltzmann distribution, how often this is going to occur. And again, that's where we can determine activation energy. And so let's say we have two molecules, we'll call this A and B, and I were to launch A at B, what we'll find...
Okay, now this is a demonstration, and there's A, molecule A, and there's molecule B, and he's going to pull this, whatever this is, back and let go of the molecule and try to see if he can make it react. And then this is the temperature. You can increase the temperature on this side.
Is that if I don't give it enough energy, then there's not going to be a chemical reaction in this one simple collision. In other words, you require a certain amount of energy for that reaction to occur. So it's kind of based on temperature. If I increase temperature, I can have more reactions. Also, if I fire it off center like that, then they're not lined up properly, and there's not going to be a reaction as well. And so with each of these collisions between all the molecules, you have to make sure that you have proper energy and you also have proper orientation. But if you do, then we can fire off that reaction. In other words, we've exceeded that activation energy. And so this could be in a unimolecular when we have just one molecule turning into products. It could be bimolecular where they're running into each other, or it could even be termolecular. We have three things coming together at once. And so all of these are based on the number of collisions that we could possibly have. And so the Maxwell-Boltzmann distribution explains how much energy we have to put into a system for that chemical.
Okay, we do not have to know the Maxwell-Boltzmann distribution, so I'm going to kind of go forward through this. All it's basically telling you is that if you increase the heat, you're going to increase the number of effective collisions. All right, there's that picture again. We did this in class. I just wrote it rather on your notes. There's joules, the reaction. The delta H at the heat of the reaction. There's the two ABs for the products. There's the A2 and the B2 reactants. And this is where we drew the activated complex that was unstable. All right. Now we're going to watch this one because this is a cool video. This video shows you what the activated complex looks like in this particular reaction. In other words, the activated complex in the middle, in the transition, has a different color than the beginning and the ending parts of the video. So I want you to watch this one. Here we go. All right, this is the very beginning. We have reactants. They're not added together. Time has not started with this reaction. Your A2 and your B2 are in separate places. Now, what you cannot tell by looking at this video is there's a magnetic stirring mechanism right down here. It's like a little bar that turns around and around, causing this to stir up, which that increases collisions. Because remember, stirring increases collisions, and it's something that increases effective collisions for reactions. Alright, see, the activated complex on this reaction is actually green. The beginning color was pink. So looking at this one, is it endothermic or is it exothermic? Well, you'll notice that the energy of the products is lower than the energy of the reactants. So this is also exothermic. And the comparison between this area, this line, and to the top of the hill, would be your activation energy. Alright, that's all we're going to do for here. Alright, and that brings us to rates of reaction. And when we get to the rates of reaction, we're going to be talking about what can we do to increase the number of reactions that happens. This is a graph that starts you off showing that the very top here, this is the very beginning before anything happens. So at the top we have H2 and I2. This is concentration now on the side, and molarity, which is moles per liter. So at the beginning we have only reactants and we have no products. This blue line is the increasing of the products over time, and the red line is the decreasing of the reactants over time. So here, delta H2, the concentration of H2, these little brackets mean concentration. It's showing you that the concentration of the hydrogen, is the change in the concentration of hydrogen in this little small area over the amount of time. And this is showing you the change in, remember delta means change in, the concentration of HI, hydrogen iodide, over time. I could have looked at it closer. I don't know why I didn't. All right, so here are the 5 most important factors in affecting reaction rates. Okay. I'm not going to watch this video in lab. We'll probably have them, we'll watch it together in another part. So different ways to increase reactant rates. First of all, things that affect it are the nature of the reactants. That means just what they are. This first video talks about what kind of elements on the periodic table. Remember that cesium was super reactive and exploded the bathtub because everything in the first column has only 1 valence electron and it wants to get rid of it very quickly, so it reacts very quickly. But other things like noble gases where they already have 8 valence electrons, they have their full octet, they don't react at all. So part of the things that affect how quickly reactions happen is what are the actual electrons and atoms that you have in play. Okay. The next thing is concentration. High concentrations increase the rate of reaction. But generally, by how much, it depends on the actual reaction rate. The actual reaction itself. Sometimes increasing the concentration doesn't affect it. Temperature. A rule of thumb is that a reaction rate doubles for every 10 degrees. So if you increase the temperature, you increase the reaction rate. Now why? Because I'm increasing the temperature, I'm giving it more energy, and they're running around faster and they're hitting each other more quickly. So normally, the higher the temperature is, the faster the reaction is going to happen. Surface area, just like when you dissolve things, the more surface area there is, the quicker it is for the 2 particles to get to each other. And then the presence of a catalyst can also affect a reaction rate. And so what we're going to do now is kind of talk through these processes using a physical demonstration with people. So the video should be paused at this point. Someone pause it right here, or the Prezi is paused at this point. And then after that, that will be the end of lab, and we will continue this discussion about things that affect reaction rates in the next class. Good luck.